Hi everyone, this video and the following two videos are going to be all about finding displacement, velocity, and acceleration from graphs. It's not my favorite topic, but it's pretty standard in the physics curriculum, and so we're just going to go over it and get it over with. A lot of students like it, so maybe you'll like it. I hope you do. So average velocity, well actually let's talk about the subject of this video specifically is average velocity and average acceleration from a graph. So average velocity is the slope of the secant line on a graph of displacement versus time, and average acceleration is the slope of the secant line on a graph of velocity versus time. Pretty simple. The real purpose of this video is leading up to finding the instantaneous velocity and instantaneous acceleration from a graph, which really is a very similar method. Okay. Many students find it easier to grasp the concepts of displacement, velocity, and acceleration in 1D motion by graphing them. Additionally, analyzing graphs of displacement, velocity, and acceleration occasionally pops up on standardized tests, and personally, while I find that graphing these functions is conceptually helpful, there's rather little new content here. Again, the big new content is going to come when we determine the instantaneous velocity and acceleration from graphs in the next video, and then the following video will be helpful as well. We're going to cap off these videos by deriving a very important equation that's really kind of going to launch the mathematical portion of this course. Okay, so how do you find the average velocity from a graph of displacement versus time, or x versus t? Recall that we had defined the average velocity as v average is equal to delta x over delta t, which was x2 minus x1 over t2 minus t1. I've made a couple of minor changes to the formula that we'd previously seen. So previously, it was v average with a vector sign over it is equal to x final minus x initial divided by t final minus t initial. And the x's had vector signs over them as well. Don't worry about dropping the vector signs. As I said, we commonly do that in one-dimensional motion because the vectors just have one number and so they look like scalars. And the subscripts have changed a little bit, but it's still, a final time and an initial time. Okay, so recall from your math classes that the slope of a line is slope equals rise over run, delta y over delta x, y2 minus y1 over x2 minus x1. I hope you can see why I've changed the subscripts up here to 2 and 1, because these formulas look a lot like one another. So these formulas are so similar that they suggest a method for finding the average velocity from a graph of displacement, or x, versus time, t. So what we'll do is we'll identify the two times of interest, t1 and t2. These will define your time interval. Adjoin the points t1, x1 and t2, x2 with a straight line. This is the secant line. That's just the mathematical vocabulary word for it, a line that intersects a graph at 2 points. And compute the slope of this line. This is the average velocity over the time interval from t1 to t2. So here's an example. Find the average velocity from A, 2 hours to 0 hours to 2 hours, 2 hours to 5 hours, B, and C, 0 hours to 5 hours from this graph. All right, if you look back at the previous video on where we defined the average velocity, you'll see that we covered a very similar problem here, and the only real difference is that the information in this problem is presented to you in this graphical way. But you're going to run through the exact same calculations that you did before. So here's what we're going to do. For part A, it asks for the average velocity from 0 hours to 2 hours. So I see that at 0 hours, it has 0 displacement. And at 2 hours, it looks like it's at 2 miles. And the way that I wrote this problem statement is that, yes, it is at 2 miles. It's a little bit unclear because I'm not a very good artist. But we're going to adjoin these two points with a secant line. So just draw a line that goes through both of them. You can extend it farther. I kind of recommend that you do. It can be helpful. But for these numbers, for these kinds of problems, what we'll end up doing is just working with the numbers that were given to us directly. So I'll show you what that looks like. Let's find the rise. it went from 0 miles to 2 miles, so 0 miles to 2 miles here. And so our rise is 2 miles. Let me maybe even be a little bit more clear. In our math classes we do y2 minus y1 in the numerator for the rise. Well, y2 is 2 miles and y1 is 0 miles, and so we do 2 minus 0, and that gives us 2 miles. And the run is 0 hours to 2 hours. So again, taking the final minus the initial would be 2 hours minus 0 hours, and it's 2 hours. Okay, that means V average equals the slope equals rise over run equals 2 miles divided by 2 hours, which is 1 mile per hour. All right, I don't actually care about this middle stuff. It's pretty well understood that that you've taken the slope of the secant line. Well, that's it. That's part A. That's our answer for that part of the problem. Part B asked for the average velocity from 2 hours to 5 hours. So we'll draw that secant line. So at 2 hours, it's here at 2 miles. And at 5 hours, it's at 20 miles. Draw the secant line. And again, you can extend it through those points. I'm going to extend it downwards even a little bit. That's going to be more important when we talk about instantaneous velocity. You'll see that in the next video. But again, we compute the rise and the run. So the rise goes from 2 miles up to 20 miles, and so it's 20 minus 2 is 18 miles. And the run is from 2 hours to 5 hours, or 5 hours minus 2 hours, which is 3 hours. Okay, and that means the average velocity from 2 hours to 5 hours over this time interval is the rise divided by run, which is 18 miles divided by 3 hours, which is 6 miles per hour. Again, not especially difficult, I hope you think. Okay, and then part C, if you go back and look at the problem statement, asks for the average velocity over the entire time period. Well, we started at 0 miles and 0 hours, and we ended up at 20 miles and 5 hours. And so let's compute the rise over here. Final displacement was 20 miles, and the initial displacement was 0, and so that's a rise of 20 miles. And the run is 5 hours minus 0 hours, which is 5 hours. All right. That means the average velocity is the slope of this. Oops, I never actually drew the secant line. You don't really need to when you're working with these points directly, but it's a good idea to draw it in, because when we work with instantaneous velocity, you'll have to draw it on the page. Okay, so where were we? The average velocity is the rise divided by the run, 20 miles divided by 5 hours, which is 4 miles per hour. That gave us the average velocity over the entire trip, okay, from 0 hours to 5 hours. Okay, let's briefly talk about average acceleration from a graph of v versus t. Our formula for average acceleration was a average is equal to delta v over delta t, which is v2 minus v1 over t2 minus t1. Again, this is a little bit different from how it was before. Previously, it was a average with a vector sign over it is equal to v2 minus v1 over v final minus v initial. V final minus v initial divided by t final minus t initial. And those v's had vector signs over them. Okay, so I just have made the same changes I did with the average velocity, which we covered a couple of pages ago. we drop the vector signs because these don't look very much like vectors. And the subscripts have changed from final and initial to 2 and 1 because this also looks like the slope formula from your math classes. Slope equals rise over run, delta y over delta x, y2 minus y1 over x2 minus x1. You can find the slope, you can find the average acceleration or the average velocity. So we can use the exact same method that we used to find the average velocity to find average acceleration, only this time we're using a graph of velocity versus time as opposed to displacement versus time. Be careful. If a question asks you to find the acceleration from a graph of displacement versus time, that's not something that you can do at this point. We'll talk about that in a couple of videos. I think we'll talk about it in the next video, in fact. So identify 2 times of interest, T1 and T2. Adjoin the points T1, V1 and T2, V2 with a straight line, and compute the slope of this line. And this is the average acceleration over the time interval from T1 to T2. So here's an example. Find the average acceleration from 2 to 14 seconds using the graph below. We're given velocity as a function of time, so that's good. We need to be working with velocity. And let's let me change the color here. Okay. So we're going to draw our secant line. So again, to be clear, this is 2 seconds to 14 seconds. Note that the graph is kind of wavy and it, velocity is increasing and decreasing. Same was true back in this example. The displacement was increasing and decreasing. That's okay. We don't need to know anything about the velocity in between 2 seconds and 14 seconds. All we need to know is that its value at 2 seconds and its value at 14 seconds, and that gives us enough information to solve the problem. So draw your secant line, goes through those 2 points, goes through some other points as well, but don't worry about that. I'll just clean this up. Let's delete these orange dots. And find the slope of that secant line. So let's let me draw a triangle right here. And here's the rise. The final velocity was 2 meters per second, and the initial velocity was 5 meters per second. Final minus initial gives us 2 minus 5 is negative 3 meters per second. Be careful about that. So the rise is negative 3 meters per second. I trip up with that every now and then, but please note that this is a downward sloping line, and so it better have a negative slope. And so you better get a rise of negative 3 meters per second. The run, meanwhile, we ended up at 14 seconds, and we started at 2 seconds. And so that is a run of 12 seconds. Okay. And so our average acceleration, our average acceleration is the slope, which is the rise over run, which is negative 3 divided by 12, which is negative 0.25 meters per second, or meters per second squared. All right. And again, I don't really care about the middle calculations. If you want to remind yourself of that, that's fine by me, but I don't think I need to see it on the page. And that's it. There's your average acceleration over this time interval from 2 seconds to 14 seconds, determined entirely from the graph. We drew a secant line, we found the slope of it. Pretty straightforward. Again, you're actually just doing the same thing that you were doing previously when we defined the acceleration or when we defined the velocity. So there's really no new information in this video in particular. What you're going to take from it, though, is just kind of the overall graphical procedure, because when we talk about the instantaneous velocity and instantaneous acceleration in the next video, that's going to be very similar to what we're doing here, and as long as we're not using calculus, there's no analogous way to do it just with numbers on the page. So I'll see you for the next video. Bye bye.